Greetings, in this video we'll cover the centralizer of a group. So let's take a group G, and the centralizer of an element A in this group G will be denoted as C. So we're working with centralizer notation, namely denoted as C sub G of that element A, where A belongs to G. So the centralizer of A inside group G, maybe this is not practical already here, will equal, to be defined using set notation, it will be all the elements X in G, or the elements in G, such that they commute with this A that's also in G. So now I define it for one element. It can be also defined for an entire set. That would, for example, be, instead of lowercase a, it would be capital A. That would denote some subset of the group G. And we would be looking at centralizer, would be basically the set of the elements that commute with all these members of this G's subset. But it's easier to illustrate it just with one element. So what we're talking about is when we have a centralizer of element A in G, it is some element A in G, and we're looking for all other elements in G that will commute with this element A. So if we take an example to be the symmetry group, on 3 letters, we can list the permutations in permutation notation. So these are all the elements of the symmetry group on 3 letters. By the way, the order is 6 elements. The reason is because always the index factorial is the order of it. So we've got these 6 permutations. The operation for this group, by the way, is function composition. This permutation notation is just the way to denote the bijective functions, the individual bijective functions, which are these so-called 6 permutations, which are the 6 elements of this group. Now, if we consider this 6th element, for example, this 6th element, the permutation that goes into 3, 1, 2, then we can look at the example of a centralizer in its case. So let's consider the element being the permutation 1, 2, 3, 3, 1, 2, which, by the way, in cycle notation will be, we can go like 1 goes to 3, 3 goes to 2, and 2 goes to 1. So it's 1, 3, 2. That's in cycle notation. It's the same thing, but we denote instead of permutation notation, where each element is mapped to its image, we just do it in cycle notation. Okay, so if we want to look for the centralizer of a particular element in that group, in this case it's centralizer in the group S3 of element A, which will be the cycle 1, 3, 2, a different way to denote the permutation that goes into 3, 2, 1. We will look for the elements that commute with this element in the group S3. So looking for what elements will commute, in this particular case depends on the group we choose. In this particular case, we can use the general knowledge we have about symmetry groups. So it will be a set. It will be a set of those elements that do indeed commute. For practicality, I will write them in cycle notation, although the individual elements we had written in permutation notation so far. So we're looking for the centralizer of the element 1, 3, 2, of the cycle 1, 3, 2 among these 6 permutations in S3. And knowing that the cycle notation is just a different way to write what we have here in permutation notation in these 6 elements, I will write the members of the centralizer also in cycle notation to save space on the screen. So the first element that could come into mind is the same element itself. If we commute two elements and they're both the same, we cannot distinguish between their order. Therefore, they will be abelian to each other. So the first example we can think of is the element itself, the same cycle. Another one that could work is, for example, the inverse of 1, 3, 2. And the inverse of 1, 3, 2, namely, turns out to be the cycle 1, 2, 3. So that's the inverse. Why? Because when we have an inverse put in operation with that original element, it will produce the identity, and no matter what the order of them is. So we could switch the order of the operation, still the identity would be the result. Therefore, the inverse will commute with that original element. So now we can look for the third one, and the third one, well, we cannot write using a free cycle in this case, because it will be the identity of the permutation, which is the permutation, the first permutation in the list. That's 1, 2, 3 and 1, 2, 3. But in cycle notation, we don't write one cycles, which this one will have to be written by. We leave out one cycles because they don't interfere with the other cycles. They don't lead to any change. But just to denote it here, I will write it that way. So it's a set of 3 1 cycles. That's the identity permutation. It cannot be written in other ways, and because there's this general tendency to just not mention one cycles where nothing would be mentioned, but to write it, it's written here. Now we can check at least if the statements we've come to have been true so far. There's probably no reason to check the commutativity of putting the same thing with itself in operation, because there's no way to distinguish the order in any case. But we can at least check the inverse, if the inverse actually is the inverse. So 1, 3, 2 is the cycle whose centralizer we're looking for, and we can put it into operation with this 1, 2, 3, which should be its inverse. And we can write the result in permutation notation again. So 1, 2, 3 up here. So how this is carried out is cycle multiplication, which I had covered in a different video in the past. So for example, 1 goes to 2, 2 goes to 1. So that's 1. We want to have the identity. That's how we check if it's actually the correct inverse. 2 should go to 3, 3 should go to 2. That's also right. 3 goes to 1 and 1 goes to 3. That's also right. So yes, it produced the identity, and when we produce the identity, we know that it's the inverse. And if we do it the other way around, it should also work. Alright. And then the identity element will not change the element it's applied to. And again, the order of this operation won't matter. So either way, it won't change the result. So these 3 are the elements of the centralizer for the cycle 1, 3, 2 in this group of 6 permutations. So just to sum it all up, when we are talking about the centralizer, we are talking about the elements in the group G which commute with a particular chosen element that particular centralizer we are linking to. It can also be a set, so then we will be talking about the elements that commute with all these elements of this subset of G. In this case, for simplicity, we just work with one element, but if instead of the lowercase a, we for example had an uppercase A, it would be a subset of G. It would be actually a set consisting of more elements. Then we would be looking for all the elements in G that commute with all of these chosen elements in that set.